I think most of you noticed that the title, well, is an adaptation of a very well-known book by Dedekind. And well, sorry, I mean, I will not reach the depths of the analysis Dedekind gave for his topic when I speak here about consistency proofs. Still, one of the aims of this talk is to give a reflection on the rationale, the philosophical rationale in particular, why we are pursuing consistency proofs. And I will do that in a historical perspective. So I will give you a lot of citations from mathematical logicians over the time, what they thought and what were the aims of consistency proofs, but I mean, reflect that or complement that with a modern view. I will not give you much mathematical details, but I hope that the experts in the audience, which know enough about mathematical logic, can fill in the technical part. However, I try to address where and when the mathematical part, so to speak, interferes with the philosophical interpretation. Okay, so let me start to give you a short overview of this lecture. I will start with the problem which arose around 1900, so more than 100 years ago. And it was in particular David Hilbert, by that time one of the world leading mathematicians, who took a challenge up. I mean, in particular, he saw, well, not everybody saw the problem. And actually, Hilbert started quite early, around 1900, immediately, let's say, to look for a solution of the problem. We will see he didn't find an easy way. It was, in fact, Poincaré, should I say, the other world-leading mathematician of that time, who rose an objection. But independently of that, in the 1910s, intuitionism came with another problem, which actually initially was not considered in the same way. And so that triggered a development of mathematical logic, in particular in the Hilbert school in Göttingen from the 1920s on, which comes under the name Hilbert's program. And if you ever have heard of it, you most likely also have heard that Gödel, Kurt Gödel, with his famous incompleteness theorem, showed that this program cannot be executed in the original way. However, Hilbert, by that time already very old, acknowledged, in some sense, that Gödel put an additional challenge to his program. And, well, he revised the starting point, so to speak, as we will see, from the 1931 on. And after that, we now speak of Hilbert's revised program, which in that way was not carried out, or, I mean, Hilbert was too old to contribute to it, but there is Gerhard Gentzen, who came up with his famous consistency proof of arithmetic, which actually is a prototype of consistency proofs we want to consider here in 1936. But as we have Gödel around, we have to discuss, I mean, what actually is going on here, and we will devote some time to discuss the philosophical rationale of Gentzen's proof and somehow Hilbert's revised program in general. And then I will shortly sketch, but without any specific technicalities, the modern developments, and finally describe the state of the art today, and finish somehow with answering the question we have here in the title of the talk. Okay, so after all, I should say, we'll 1.25 centuries of research, mathematical logic we call here, and I hope that the time is enough and that you will enjoy. So where all the problems came from. Let's start with Georg Cantor. I hope also, a well-known name, who actually conceived set theory as a new mathematical discipline. And it was considered by that time with some reservation. However, it was in particular Hilbert and Minkowski and Königsberg which took it up, which realized that it's a very fruitful framework, and actually for all areas of mathematics. And there's one point which is could not be stressed enough, that before Cantor, the mathematical disciplines were really separate ones: arithmetic, analysis, geometry. And today we have a common language. We can say at the end, it can all be recast in set theoretic terms. Of course, we don't do that as working mathematicians in our daily work, but it can be done, and somehow this was new. And let's say there's one particular instance where it was important. It was the reduction of the real numbers. Reduction, well, that's to be discussed, to the natural numbers, or let's say using the power set operation to obtain real numbers out of natural numbers. However, soon it turned out that there are problems with set theory. And you probably, you may know the Russell paradox. And actually, it was by the same time found by Ernst Zermelo, who was at that time a student of Hilbert in Göttingen. Zermelo didn't publish it, so it's quite correct to call it Russell paradox, but it was truly independent, observed that you run in trouble if you define, or let's say if you consider, I should say, the set containing all sets which do not contain itself. Now, in modern notation, can be written like that. And this is the usual comprehension notation. And now you have to ask, does R belongs to R? Well, just suppose it would belong to itself. Now you rewrite the right side by definition, but now this is simple comprehension. So R is in this set if it fulfills the condition here. So it would be, it would mean R is not in R, and we have a contradiction. And contradictions are not good in mathematics. And why? It was not even the only problem. So already before Russell and Zermelo, Cantor, but never published it, found that the set of all sets cannot be a set. So we should not call it. By the way, a modern solution is to call it a class. The class of all sets is not a set. But by that time, there were no class concept around. There were only sets. And Cantor had no problems with it. He just said, okay, that proves that it is not a set. And Burali-Forti, that was actually the first published one, considered the set of all ordinals. And you see that that cannot be. Then we have Russell-Zermelo. And there were some more, even one specific, a variant of Cantor's paradox, which Hilbert himself found. And so that might be one of the reasons why he was so interested in this issue. Now, in 1905, actually maybe later, it's a marginal in lecture notes of 1905, Hilbert noted two quite good questions. Why is the totality of all sets an impermissible collection? Why is the set of all real numbers a permissible collection? Of course, let's say we don't want to give up the real numbers in mathematics. But we also know that we cannot have the set of all sets. By the way, why we cannot have it? Because then you can apply power set and you would get a set which has higher cardinality, but the set of all sets, when there cannot be anything of higher cardinality. So there's a specific point here, I would say. We all know that we cannot have the set of all sets, the totality of all sets. It just follows from Cantor's theorem. But that doesn't answer the question, why? And well, this why, so the reason why one is allowed and the other is not allowed, will be soon coupled with the question of consistency. But maybe that even is a little bit controversial, as we will see. Okay, so here we have the problem. Now, Hilbert saw that this is really a problem because it put in question mathematical reasoning as such, in particular the concept of proof. And he expressed that very aggressively in 1917, also in a lecture note. If we can only check the admissibility of a mathematical proof by its result, we do not need a proof at all. So this is against Cantor, who said, okay, just let's build these sets. And then when it turns out that they lead into contradiction, we know that they are not permissible. And Hilbert says, no. It doesn't help that we know that at the end. We have to know it at the beginning, that it will not lead to contradictions. But how could we know that? And so he realized that proofs themselves should be the object of investigation. And that's quite new. Before, proofs, mathematical proofs, even in Euclid, are just informal presentations of lines of thought, as we could say. And Hilbert, and this is out of a lecture on axiomatic thinking, we must, this is my conviction, make the concept of specific mathematical proof itself the object of an investigation. And here you see, that is the base, for proof theory in a literal way. Now, there's a specific twist, now not supported by a citation, but much later it became clear. This investigation should be, again, a mathematical investigation. So for Hilbert, it was clear from the very beginning that it's a mathematical task. It's not something we hand over to philosophers. Well, if you investigate mathematical objects, you are already doing what is now called meta-mathematics. But that term, by the way, was coined by Brouwer, and I think rarely used, if at all, by Hilbert. Hilbert actually coined the term proof theory, and he even spoke about more or less Hilbertian proof theory. So he was well aware that that was his invention. Now, so we have to mathematize proofs. And before proofs, let's say we have to mathematize mathematics as such. And fortunately, by that time, Hilbert already found an attempt for that. Frege's Grundgesetze der Arithmetik. Gottlob Frege actually provided us with the first satisfactory formalization of quantifier logic. However, his attempt to build in mathematics into this framework failed heavily because it was actually subject to Russell's paradox. So Russell found it by reading the Grundgesetze der Arithmetik and wrote to Frege, and Frege admitted that he cannot overcome the problem. Zermelo actually found it completely independent by looking, I think, to set theory. Now, Russell actually took up the challenge together with his colleague Whitehead, and they wrote this 3 volumes of Principia Mathematica. That actually is a type theoretic approach to encode mathematics one could even say purely a logical framework. However, it suffers from the reducibility axiom, if you ever have heard of it, because typing, well, it doesn't work fine without reducibility. I mean, you still get a nice system, but you don't get the real numbers you want to have as mathematicians. And actually, it says, I mean, it's a question who read the Principia Mathematica. If you look at the book, it's full of formal derivations in dot notations, very hard to read. But it was scrutified in Göttingen. So there were one student of Hilbert Behmann who wrote a dissertation about it. And well, Hilbert himself came to the conclusion that that approach doesn't work because of the reducibility axiom. And by the way, the infinity axiom is also a problem there. So then, with a much more modest approach, but let's say with the kernel of what we do in logic today, Hilbert and Ackermann published the first modern textbook on logic, Grundzüge der theoretischen Logik, in 1928, which, I mean, by accident, does not mention the real author, so to speak. It was Bernays who developed all the technicalities. But, I mean, he didn't wrote that book. He wrote with Hilbert, the Hilbert Bernays, which has a different story. But it's essentially first-order logic as we use it still today. The point here is that it somehow admits that the mathematical entities are not reduced to logic, but have to be added axiomatically. So that's much less in the philosophical aim than what Frege and Whitehead-Russell tried. Still, let's say it's what we have today, and that is the point here. It's what we need to formalize mathematics. I mean, actually, to have the mathematical objects as non-logical parts, that's essentially due to Peano. That's the reason why we speak today of Peano arithmetic. Now, it was even Gödel, however, in an unpublished manuscript, who admitted that this was perfectly solved the problem. So the first part of the problem has been solved in a perfectly satisfactory way, the solution consisting in the so-called formalization of mathematics. And so if we do consistency proofs, we need that. I mean, otherwise we don't have a technical starting point, but that's done. And it didn't come for free, but of course, let's say we heritage it, and now we can think of mathematics in a potentially formalized way. By the way, Hilbert was not a formalist. I mean, he didn't say that we should formalize all of mathematics, not at all. He wrote a book on imaginable geometry, where the word axiom is essentially not mentioned. But it was the formalizability which shows that in principle you could formalize it if you need it, and you need it when you want to do consistency proofs. So, and it was already in 1900 that he made that quite explicit, what was his aim. The second problem is the consistency of the arithmetical axioms. And here, just, I mean, from the translation, which were already given in 1902, I think, when we are engaged in investigating the foundations of a science, we must set up a system of axioms which contain an exact and complete description of the relations subsisting between the elementary ideas of that science. And here it's for arithmetic. But above all, I wish to design the following as the most important among the numerous questions which can be asked with regard to the axioms, to prove that they are not contradictory. That is, that a definite number of logical steps based upon them can never lead to contradictory results. A direct method is needed for the proof of the consistency of the arithmetical axioms. So the point here is that is the idea of consistency proof in the second paragraph. Now, when he speaks about a direct method, the point was that he had already published his foundations of geometry, and were able to reduce the geometric axioms to the axioms of analysis. So one point here, Hilbert refers to second-order arithmetic, which amounts to analysis. So if the problem is called the consistency of the arithmetical axioms, in modern understanding, this covers analysis and a fortiori geometry. But he was well aware that there he cannot reduce it further. In particular, nevertheless, that he still tried it a little bit. I mean, it turns out that the logicism, so to reduce the arithmetical axioms to pure logic, that eventually fails. Okay, so how could a consistency proof look like? And this now sketches what Hilbert did by that time. So the first observation, it's absolutely fundamental. Proofs are finite objects. So if you have infinite proofs, they are not proofs in our normal mathematical understanding. So they may be arranged as finite lists or trees of symbols, and these arrangements follow fixed rules. Now the goal is to prove that these finite syntactical objects can never have a false formula, for instance 0 equals 1, as last element. And 1 is enough, and let's say if 1 is excluded, all false formulas are excluded by the logical rule of X falso quod libet. So if you have one false formula, you get all formulas, and so if one formula is not provable, also other false formulas cannot be provable, because otherwise with them you would get the one in question. Now, in this view, consistency of a formal system is a purely combinatory problem. And actually, I mean, in modern unprovability results, the connection with combinatorics in mathematics is quite strong. Because in particular, if you think of trees, but even lists, I mean, that are combinatorial objects where you have fixed rules, but you may apply one or the other rules. And so you have choices, but somehow at the end, you consider the possibility to arrange finite graphs, for instance. I mean, it's amazing. So that gave some rationale why consistency proofs could work. And he was sketching one. It's quite interesting because, I mean, the method he uses, it's not the modern one, it's really working with invariance, which was one of his main topics in ordinary mathematics. So 1904, 4 years after the Paris lecture, he sketched such a consistency proof in his talk at the International Congress of Mathematicians in Heidelberg. But, I mean, it was a toy example. I mean, it was arithmetical with some equations, but it still didn't include induction. Well, and that's the talk, it's said, was not understood by many people, but it was most likely read by Poincaré. And Poincaré objected to the very idea of consistency proof, as they would result in a vicious circle. So that no false formula can be generated requires an inductive argument. So, I mean, if you really want to see, so all lists of symbols never will result. So this universal quantifier, I mean, can actually be approached only inductively. So you start with a short proof. Or you consider all proofs of length 0, that are the axioms, then of length 1, length 2, and you could do, I mean, imagine that inductively you then prove something for all proofs, namely that they never result in a false formula. But in arithmetic, all the point is to justify induction, and here you would need induction. So you have a vicious circle. One will need induction to justify induction. And actually this argument impressed Hilbert. For that we have testimonies, and I mean, he stopped working on that for a while. And somehow why he was not working on that, the problem became bigger. Because Brouwer, a Dutch mathematician, wrote a thesis in 1907, still in Dutch, which had not an immediate impact, but soon after published his ideas, also in German. And he questions quite generally more mathematical or even logical concepts. So what he said, that the tertium non datur, phi or not phi, may not hold for infinite domains. And I say that's a very fundamental logical law, which I mean goes back to Aristotle in one or the other way. And I mean it's used in mathematics in particular to justify indirect proofs. So why that should not hold? Well, Brouwer had some arguments because I mean effectively I mean today we can say it, you cannot implement it on a computer. If you don't know which of these two sides hold, a computer program which should deal with this decision, I mean, does not know which way to go. So that was one of the points. And another was that the real numbers are not representable by the power set of the natural numbers. So Brouwer was heavily I mean, one should say, didn't even consider Cantorian set theory as a valid framework. And so he had a very specific idea how the real numbers actually needed for geometry might be generated, but let's say not in the way as Hilbert did it actually already in the Grundlagen der Geometrie. Now, Brouwer dubbed his approach intuitionism, and then Hermann Weyl joined him. And it is even said that that was particularly hard on Hilbert because Hermann Weyl was his best student. By that time, he was professor in Zurich, but I mean, he was on place one to success Felix Klein after World War I, but he declined most likely still because of the economical situation in Germany. But then in 1930, actually Hermann Weyl became successor of Hilbert in Göttingen and left in 1933, again because of the political situation. But that Hermann Weyl joined Brouwer, and actually there are nice expressions. So Weyl wrote in a mathematical paper, Brouwer, that is the revolution. And he accused analysis in the sense Hilbert were doing it, let's say, via the power set of the natural numbers. Analysis would be a house built on sand. So now Hilbert really saw it as his obligation to counter these attacks. And by the way, with Hermann Weyl, more or less, he had success. So Weyl became more modest when he became older. And recognized that also Hilbert's view is legitimate. But okay, so out of this conflict, it emerged Hilbert's program. And that's essentially, I mean, it's 1917, his talk on axiomatic thinking, where he announced it is, and then in the 1920s, he and his school in Göttingen developed what we called Hilbert's program. In fact, it was technically, it was particularly led by Paul Bernays, who we will listen to also in the very end, but okay. So he distinguished the mathematical meta-theory, which is used to carry out a consistency proof, from the mathematical object theory, which should be shown to be consistent. So that is the fundamental step. And now the meta-theory must not be subject to consistency concerns. And it has to address all concerns of Brouwer. And here he chose finitary mathematics. And finitary mathematics turned out to be, I mean, even stronger than, or more restricted than intuitionism. And Hermann Weyl wrote later in the obituary, I mean, that Hilbert was more papal than the Pope compared with the intuitionistic demands. So we don't have a formal explication of finitary mathematics. In modern terms, it's usually identified with primitive recursive arithmetic, but that doesn't play an important role for the moment, and it doesn't play any role any longer after we learn of Gödel's result. But what was important, it does not presuppose infinite entities. Thus, the tertium non datur is justified in this realm. And that's important because, I mean, Brouwer criticized the tertium non datur for infinite domains. Now we do intuitionistic logic where the tertium non datur is not valid at all. However, also for Brouwer, I mean, if I have an equation with numbers, t equals s or t is not equal s, I mean, that distinction I can do, or this disjunction I can use as an axiom, because I would have only to calculate t and s, and I see they are equal where not. And that's, I mean, Hilbert took that over. In the meta theory, we can use that, but we cannot use the tertium data for infinite domains. Actually, we should avoid infinite domains in any case. Somehow, we still have potential infinity, but not actual infinity. And then, and that is the technical point, which is fundamental, it contains only very restricted induction. And that somehow addresses Poincaré. Because, yeah, you need an inductive argument to justify induction, but maybe you can use weak induction to justify strong induction. And that was the hope. And if you have this combinatorial view of finite proofs, it's not excluded that could work. They will not, but okay. Just a historical note. With respect to the later development of the personal relation between Hilbert and Brouwer, when they were close friends, at least by 1909, but then they fall apart, I mean, heavily on political issues of German mathematics, the standing of German mathematics in the interwar times. And I mean, ironically, Brouwer took position for German nationalism, while Hilbert was much more liberal or let's say an internationalist. In any case, here it is ironic that the idea of distinguishing the two types of induction was given to Hilbert by Brouwer. So it was Brouwer's idea Hilbert could use to counter Poincaré. However, that was by the time Poincaré had already died, so didn't enter in the discussion, of course, any longer. Now it comes the rationale of consistency proofs as conceived by Hilbert against intuitionism in my reconstruction, actually as a modest tolerance argument. So one uses finitary mathematics for consistency proof of classical mathematics. And classical mathematics is the everyday mathematics with the tertium datur for infinite domains, where we work normally. Now, if classical mathematics would contain a contradiction, also finitist mathematics would contain a contradiction. I mean, that is the very essence of consistency proof, of reductive consistency proofs. I mean, consistency of A implies consistency of B. B means if B has a contradiction, A has to have a contradiction. Just take the contra reciproque. And so, well, finitistic or finitary mathematics, which was intended to be intuitionistic mathematics, or being even weaker than its intuitionistic mathematics, has to be accepted as consistent by intuitive or specific word, contentual reasons. Now, Brouwer and Weil would have to subscribe 3. I mean, that was all the idea. By the way, I mean, Brouwer, his intuitionistic mathematics would not be subject to consistency proofs, because there should not be any concerns about consistency, because you see the consistency if you even ask for it by intuitive inspection, so to speak. So Brouwer and Weil would have to subscribe 3. They also would have to accept, I mean, as they have to do that, they also have to accept classical mathematics. So that was the basic idea of Hilbert's program. I mean, to convince intuitionists and everybody who has doubts about the consistency of classical mathematics, beating them on their own field. But I mean, it goes without saying that Hilbert never had doubts about the consistency of arithmetic, most likely not even set theory. Now, there is one historical point that actually, at this point, Hilbert and Brouwer spoke at cross purposes. They simply didn't understand what one or the other did. Well, maybe Brouwer understood what Hilbert was doing, but said, I mean, for me, that's of no interest. Hilbert did not argue against consistency proofs of classical mathematics, but that he said that consistency alone does not produce meaning. Insofar, he did not consider Hilbert's program as unfeasible, but that it would not provide any profit. And that comes from a very old thesis. So consistency implies existence, something Hilbert subscribed, which was questioned by Frege. But by the way, you find it on record by Poincaré. But in any case, I mean, Brouwer rejected that from the very outset. Now, this debate were never taken up, in particular by Hilbert. So Hilbert insisted, I mean, consistency does the job. However, there will be a very specific twist on the very last slide, if you remember that then. A twist which I think Brouwer was not aware of. Okay, but we will follow here Hilbert's line. And, well, then Gödel came across. Actually, Gödel worked somehow on Hilbert's program. It was his intention to show it, to fulfill it, but while trying to prove the consistency of now analysis on the base of the consistency of arithmetic, he realized, oh, there's a problem. And that problem turned out to be fundamental. And so his second incompleteness theorem says a formal theory containing a modicum of arithmetic cannot prove its own consistency. Now, if you take that as it stands here, that would not shock anyone, because if a theory proves its own consistency, that means nothing, because inconsistent theories prove everything, so also its own consistency. However, there's an immediate corollary, and that is often not pointed out. Because formal theories are in the I mean, let's say, normal understanding monotone, it can also not be that a weaker theory can prove the consistency of a stronger theory. And let's say, starting at arithmetic, because that Gödel's second incompleteness theorem works, you need this little bit arithmetic to be able somehow to code these formalized proofs in mathematics itself. So, and this is the end of Hilbert's program as it was originally conceived. And it's also said that in Göttingen, they accepted that immediately. Because, I mean, when I said before, well, we want to use weak induction to justify strong induction, as much as the weak induction scheme is an instance of the strong induction scheme, it cannot be sufficient to prove the consistency of the strong induction scheme. Otherwise, you contradict Gödel's second incompleteness theorem. So let's take a second to reflect on that. And I mean, it's totally justified that Gödel is considered, or Gödel's incompleteness theorem, but he is considered as one of the greatest logicians of all times. And the incompleteness theorems, I mean, the first one I don't mention here, has also some relevance, but we don't want to go to the technicalities for Hilbert's program. It's the second incompleteness theorem, is one of the most important results in logic history. But so the first point is, intuitionism wins nothing with it. In fact, Brouwer commented only very shortly that he was not surprised about that. However, if you don't have the incompleteness from the first incompleteness theorem, you have built in Brouwer's theory if you don't have the tertium non datur. Now, the problem, or actually, I mean, the first incompleteness theorem, which I didn't even show you here, poses a specific challenge for intuitionism. Because what it shows is that when you have a theory of arithmetic, if you know it, think of Peano arithmetic, there's a formula which cannot be proven nor refuted, which means that there are stronger theories, PA plus this formula, let's call it G, and another PA plus this formula non-G, which are both consistent. And with modern tools of model theory, we know that there are non-standard models which fulfill usually this non-G, and the standard model fulfills the G. In any case, there is some kind of meaningful mathematics beyond Peano arithmetic. And we have a good intuition which, let's say, when we use the term standard and non-standard, let's say that we want to have the non-standard, but that we want to have the standard models of arithmetic to be investigated, not the non-standard ones. In any case, let's say, intuitionism cannot tell us anything about these stronger and stronger systems we can build. And classical mathematics can do, well, actually what it tells us both is meaningful, but it has different meanings. And then it's the question how to choose. So for arithmetic, we know, but for instance, in set theory, and that was also Gödel, I mean, who did one part, Cohen the other part, the independence of the axiom of choice and the continuums hypothesis, we have no criteria which one to choose. Actually, I would say for the axiom of choice, we might have criteria if you want, but for the continuums hypothesis, we don't know which are the standard models and which are the non-standard models. But that is a problem for us, so to speak, our intuition here might be incomplete, and set theory works on getting our intuition fixed in that areas. But somehow it's now not intuitionism which can tell us that, I mean, or let's say we don't follow the intuitionistic approach that, okay, it's consistent, but let's say that would give no meaning. In fact, we have learned to give it meaning, maybe some very weird meaning for non-standard constructions, but still, let's say, we manage with that. So, and by the way, Gödel was neither formalist or intuitionist, if you make that distinction, or not even logicist, by the way. That's logicism is over once and for all with Gödel's result, because it really shows that, I mean, you cannot even reduce higher mathematical constructions to arithmetic, so absolutely no way to restrict it to logic, with one proviso, because now we are already in the world which only lives with first-order logic. Second-order logic is a different point, and I mean that was what Hilbert initially had in mind, but it's another corollary of Gödel's first incompleteness theorem, that second-order logic is not even axiomatizable, or so that means if we want to have a proof system for second-order logic, a complete one, which really proves you all true formulas, your proofs could not be finite any longer, and that contradicts the very notion of proof as we had it at the beginning. Okay, but yeah, Gödel was somehow a realist, he admitted, or one could say a Platonist. I mean, he stayed outside of the philosophical choices Brouwer at least offered between intuitionism and formalism. And his incompleteness theorems somehow vindicate this neutral position, or even give support for the realist position in philosophy of mathematics. However, going back now to our question about consistency proofs. So is the business of consistency proofs dead with Gödel's incompleteness theorem? It might be, and some people do so, but no. I mean, there's in fact only one very small sentence where Hilbert commented on that. But by that time, Hilbert was already very old. But we will see he was still involved because he was noticing, and then it's reported by Bernays that he was angry about Gödel's result, but that then he soon took it up as a challenge and he changed his program. So, and it's the preface of the book Bernays essentially wrote, Hilbert Bernays Grundlagen der Mathematik, first volume, published in 1934. So Gödel's result shows only that for more advanced consistency proofs, the finitistic standpoint has to be exploited in a manner that is sharper. One can speculate how to understand this word sharper, schärfer in German. And of course, what it means, what it practically has to mean, one has to be more liberal. It's a question whether that fits with the meaning of sharp. But Hilbert noticed, okay, we have to change something. So with finitistic mathematics, it doesn't work. And there is a letter of Ackermann, Wilhelm Ackermann, another student of Hilbert, for instance, known in recursion theory from the Ackermann function, who wrote in 1933 when he visited Göttingen, but he missed Hilbert. And afterwards, he wrote, I was particularly interested in the new metamathematical standpoint, which you now adopt and which was provoked by Gödel's work. So there is a new mathematical standpoint, which in fact still allows to carry out consistency proofs. So what is it? Bernays reports that some years later to Lorenzen. When it comes to the mathematical standpoint and to the terminology to be used in relation, then it seems advisable to me to keep with the mode chosen by Mr. Gensen. This is forward reference. Gensen comes on the next slide. That one speaks of finite reflections only in the narrower sense. So finite reflections, that was finitistic mathematics as Hilbert had it in mind in the beginning. That's the narrow sense. That one uses in contrast the expression constructive for the appropriate extension of the standpoint of the intuitive self-evidence. So the switch, and actually it was still initiated by Hilbert, not carried out, but it was initiated by Hilbert. The answer to Gödel was moving from finitary mathematics to constructive mathematics. And well, for the moment, I don't want to go into the details about its constructive. We will see it when we discuss Gensen's proof. But yeah, I mean, what we have said at the very beginning, consistency proofs need a meta-theory. And so now you replace the meta-theory by, instead of finitary mathematics, you have constructive mathematics. And so in 1936, Gerd Gensen, also a student of Hilbert in Göttingen, I mean, essentially working with Bernays, he was able to provide a consistency proof for formalized arithmetic, so including the mathematical induction, according to Hilbert's new mathematical standpoint. So what did he do? Now, I don't want to be too formal, but I hope the mathematicians among you know it, but I mean, you can look it up. I always spoke about arithmetic. So arithmetic is about natural numbers, 0, 1, 2, plus, times, and of course, equalities. Now, Peano arithmetic is a standard formalization of arithmetic in first-order logic. Historical note, Peano did it in higher order logic, and then the situation is completely different. But here it's today given in first order logic. And so you have some Peano axioms as they are called. So 0 is not, so for all x, 0 is not successor of x. Sorry, for all x, 0 is not successor of x, means that 0 is the first natural number. There's no number before. And then you have the actually Grassmannian equations for addition and multiplication. But then you have induction for arbitrary formulas. Now, I said before, finitary mathematics was not given in formal terms by Hilbert. Now, there's an influential paper, I think, from the 70s, which proposes primitive recursive arithmetic. I mean, there are some details one can discuss about that, whether it's adequate, but for our argument here, it's perfectly okay to identify finitary mathematics with primitive recursive arithmetic. And that's usually abbreviated PRA. So that is arithmetic with induction restricted to quantifier-free formulas. And by the way, then you have to be a little bit careful with the function definitions. So you need some more primitive recursive function equations, not only plus and times. But never mind, the philosophically and technically important point is that its induction is restricted to quantifier-free formulas. And that implicitly means that you cannot address infinite domains any longer. I mean, you can, for all x, phi of x, you may still prove by induction, but this phi cannot contain further quantifiers. So the original idea could now be recast that, okay, PRA should prove the consistency of PA. And that is excluded by Gödel. So Gensen added transfinite induction up to epsilon naught. And with this transfinite induction, he was able to prove the consistency of PA. Actually, it's quite good that it's called transfinite induction. So we see that it's not any longer finitary mathematics. There is one transfinite element and it's this induction up to epsilon naught. Now, what is epsilon naught? That's a transfinite ordinal. And somehow, I mean, if you want to follow modern consistency proofs, you have to learn a little bit about ordinals, or even more specific ordinal notation systems, because they are an important tool. Now, somehow, when you saw the first infinite ordinal, omega, first transfinite ordinal, so the omega is bigger than every natural numbers, but there's no other transfinite ordinal below omega. Then epsilon naught is somehow the infinite omega tower, omega to the omega to the omega to the omega. So technically it's the least ordinal alpha with alpha equals omega to the alpha. What's the point here? How the ordinals come into the game? Well, the point is that ordinals are well ordered. It comes somehow out of this definition. By the way, there are several equivalent definitions as set theoretic objects, but I mean, we don't want to have set theory, so we have to develop a certain theory of ordinals, or as I said, ordinal notations. But when you do that, and now you have the order relation corresponding to that, I mean, as I said, every natural number is smaller than omega. Then you can start with an arbitrary big ordinal and try to go down. And the idea is, if you go down, you look for smaller ordinals, smaller ordinals, smaller ordinals. Sooner or later, you have to end up in 0. And there cannot be an infinite chain of smaller ordinals. So that's the well-foundedness. And the point here, what's all about, is that you should have an intuitive understanding that these ordinals which you have constructed will be well-founded. And if you have that, if that's your intuition, then the transfinite induction is justified. So the transfinite induction along well-orderings of order type epsilon naught is also is now also restricted to quantifier-free formulas. If not, by the way, there's it's a joke reported by Hermann Weil, who said that, oh, I mean, Gensen justifies omega induction, that would be normal induction, by epsilon naught induction. And that seems to be very weird. But the point is that it's quantifier-free formulas you consider here. So you have this transfinite element in the ordinals, but you apply it only to somehow very, very big quotes, finitary formulas. Let's say that's these quantifier-free formulas. And so that does the job. So based on the well-foundedness of epsilon naught, one obtains indeed a meta theory which should not be subject to consistency concerns. And actually, so it's not any longer finitary, but it's constructive because we are able to construct in a way Brouwer would have to subscribe it, these transfinite ordinals, at least up to epsilon. Anyway, we will still come back again why this is such a good meta theory. Yeah. And now we have it what Hilbert was wanting. This theory established the consistency of formalized arithmetic. And now take the Monos-Tollens argument. So just think of Peano arithmetic would be inconsistent. Then PRR plus transfinite induction up to epsilon naught needs to be inconsistent. But that cannot be, let's say, for Brouwer by the insights, by the intuition you have for the construction of the ordinals, and let's say somehow the innocent quantifier-free induction. Of course, let's say it comes with a price. I mean, you have to believe in quantifier-free induction. If you don't do that, if you question that, you will never ever go off ground. We come to that again. But now, let's say you reduced consistency really to something which may have an intuitive justification. And we will see a further citation of Gensen who makes that clear. Just one point here is, and this is literally Gensen, so in his manuscript, he wrote, it's in German, wo ist der Gödelpoint? Where's the Gödelpoint? So when he executed that consistency proof, he was aware, wait a moment, I have to be careful. Gödel tells me a theory cannot prove its own consistency. And so there must be something that this argument does not contradict Gödel's second incompleteness theory. And in fact, it is quite well measurable. And Gensen did that also, I mean, showing that Peano arithmetic cannot prove transfinite induction up to epsilon naught. So this additional concept, transfinite induction up to epsilon naught, is outside of the reach of Peano arithmetic. And so you don't contradict Gödel. So you actually, I mean, the point is no weaker theory can do it. So it has to be some stronger theory. So in some sense, PA plus transfinite induction up to epsilon naught is stronger than PA. But still, let's say, it's PA is not a sub-theory of PA plus transfinite induction up to epsilon naught. And what you actually did, you used some other tools, which in terms of considering ordinals, it's a little bit stronger. But still, from the intuitive point, it might be, or not might be, I think it's common sense that it's more, it's not in the risk of inconsistencies because we have this intuitive understanding for the involved inductions as they don't include quantified formulas. So here's the, I will a little bit repeat what I just said in connections with two citations. So the first one is Weil in the obituary for Hilbert wrote, it must have been hard on Hilbert, the axiomatist, to acknowledge that the insight of consistency is rather to be attained by intuitive reasoning, which is based on evidence and not on axioms. So what Weil suggests, and Weil were knowing Hilbert very well, I mean, they were very close as colleagues, as student and colleagues, one has to say. Hilbert might have had in mind that you could do consistency just out of the axioms. But, well, he had to acknowledge the insight that you need some intuitive reasoning. I mean, it came out of Poincaré's objection. So you need some intuitive justified induction to get that. Now, if you need some intuitive reasoning, it doesn't need to be the finitist one. It can be transfinite induction up to epsilon naught. If that's intuitive reasoning, it's okay. And Gensen himself commented, that's, I mean, in the context of his consistency proof, in fact, he justifies, he has very good philosophical reflections on his work. So such a consistency proof is once again a mathematical proof in which certain inferences and derived concepts must be used. So that just means also the meta theory is a mathematical theory, and it uses inferences and concepts. Their reliability, especially their consistency, must already be presupposed. And now the point which some philosophers wrongly put under Hilbert's aim, there can be no absolute consistency proof. So Hilbert was never, according to Hilbert, maybe he was dreaming of it at the beginning, but he soon acknowledged there is no absolute consistency proof. So you always reduce it to something. But this something it will be presupposed, and now is something you rely on it. The reliability is presupposed. And what now happens is just that Gensen used this transfinite induction up to epsilon naught, whose reliability is presupposed. So a consistency proof can merely reduce the correctness of certain forms of inferences to the correctness of other forms of inference. So what he did was reducing arbitrary induction somehow to transfinite induction up to epsilon naught, but for quantifier-free formulas. I also say normal induction is accordingly reduced. And so the rationale of a consistency proof relies on the reliability of that meta theory. In this talk, I gave you, go back first. Here, the specific point for the reliability is the constructiveness of epsilon naught, or the well-foundedness, we have to see. Now, okay, so while intuitive finitist reasoning is not enough by Gödel, there might be other intuitive reasoning which one may consider foundationally safe. And again, Gensen, it remains quite conceivable that the consistency of elementary number theory can in fact be verified by means of techniques which, in part, no longer belong to the elementary number theory. So transfinite induction up to epsilon naught does not belong to elementary arithmetic. It's transfinite, it's outside of PA, but which can nevertheless be considered to be more reliable than the doubtful components of elementary number theory itself. So transfinite induction up to epsilon naught is more reliable than the doubtful components. The doubtful components here, it's the universal quantification in the induction scheme. Okay, so this was done successfully, and by the way, I think also accepted by most of the people. By that time, that we have here a consistency proof in the spirit of Hilbert. Now, it's not even the only one. Gödel, as early as 1938, in a talk from which we have his notes, it's not a full manuscript, but it's the notes, where he considered three possibilities to go beyond. We need some other means. Which could it be? So how then shall we extend? Extension is necessary. So extension of piano arithmetic, the meta theory. Three ways are known up to now. Higher type of functions of numbers, etc. Second, the model logic route, introduction of an absurdity applied to universal sentences and a notion of consequence. Third, transfinite induction, that is inference by induction, is added for certain concretely defined ordinal numbers of the second number class. So now, if you look, these three they are all realized in all studies today, even much further than only 38. The first is Gödel's own idea, and it comes today under the name of Gödel's T, because he called the system T, which he published in a journal called the Dialectica. And so it's called the Dialectica Interpretation. I mean, that was Gödel's idea himself, but in 38 he didn't publish it. He published it in 58, only 20 years later. And then second, that comes the model logic route. Let's say, I mean, there are relations to the double negation interpretation and more generally the Brouwer-Heiting-Kolmogorov interpretation. Actually, Gödel dismisses that. He thinks that's not a good road. But the third one is the one I presented you here, and I will continue a little bit with that, with Gensen and, let's say, more generally, ordinal analysis. And so, but the point behind here is, okay, we need some extra means, but we can take other means. Philosophically, it's important that we trust them more than the theory we're looking for to prove the consistency. And for instance, Gödel's T, you have function of functions, so functionals. But it will be a purely equational theory, so you don't even have induction or something. And if you have an insight in how to compute with functionals, that might be by far more intuitive, let's say, than have arbitrary formulas, first-order formulas with a lot of quantifications. But now, let's say, you have always to look in the concrete. I mean, does that convinces you? And we will see in a minute that there are some quite critical voices if we go further. Yeah, what's going further? I mean, for arithmetic, sorry, I mean, even historically, there are only a very, very few mavericks which had concerns about the consistency of Peano arithmetic. I mean, for sure not Hilbert, not even Brouwer. I mean, after he acknowledged the formalization by Heiting, the double negation interpretation gives consistency proof for classical arithmetic based on Heiting arithmetic. Now, the point is different if we come to classical analysis, and Gensen put that on record in 38. Indeed, it seems not entirely unreasonable to me to suppose that contradictions might possibly be concealed even in classical analysis. Thus, the most important consistency proof of all in practice, that for analysis is still outstanding. And still today we don't have it. Now, shortly, let me address analysis. So before, in arithmetic, we have first-order logic with quantifiers of the natural numbers. Now we go to a second-order language with set variables, or somehow it's a two-sorted language. When it's not second-order logic we just want to have second-order quantifiers for sets. And you see it here, then you have an arbitrary formula, but x should not occur because we want to define x as the set which collects all elements fulfilling this formula phi. So there should be such a set that all its elements fulfill phi, and whatever fulfills phi is in x. Now, what's the problem with that? Actually, it's technically, I think it's rarely done in mathematical classes, but I mean, out of that you get the real numbers. So in logic courses it might be done. This comprehension scheme is highly impredicative. And what is impredicativity? Well, it means that the definition of x depends on x itself. And so you have a circle. The question is just, is it a vicious circle or not? So why that? Well, if it's unrestricted, this phi, it may contain universal set quantifications for all y. But for all y's, for all sets, so, well, you are just defining here x, so maybe you could instantiate, or not maybe, but I mean, If it's for all, it should be able to instantiate y with the new defined x. So the quantification is supposed to include the set x we are just introducing by this comprehension. Thus, the definition of x depends on itself, because I mean, if you evaluate that for all y before you even know what x is, it's not sufficient. Then you get x, but then you have to re-evaluate it. And so it's by far not clear why, I mean, is that still consistent? I mean, it's not to, I would say, it's not to see how in elementary arithmetic you could come up with an contradiction. But here, this already has a little bit, I mean, it rings the bell of Russell in the back. In fact, it's not. I mean, put it in a different way. We have very good empirical evidence that this is consistent. But how to show that? And so here, as Gensen says, we really want still a consistency proof. And in the way Gensen described it, I mean, it has to be a reduction to something we trust more than such an impredicative comprehension scheme. Well, full analysis is out of reach still today. What we can do, and here I mean gives you just a glimpse of technical developments, we can restrict that phi. So it should not be an arbitrary formula. So we somehow, I mean, it would be nice if it does not have another quantifier over sets. So the first one is pi 1, 1. So, oh, actually I should specify. Well, I mean, if you don't allow another set quantifier, then you fall back to arithmetic. Then you just have, I mean, you can build arithmetic sense and nothing happens. So, but what is it if you just have one? You have just one quantifier over sets. And indeed, if you see here, I mean, they just show it here, so pi 1, 2, then you count the quantifier switches for all existed, and so on, and so on. It turned out that that gives more and more complexity and mathematical strengths towards full analysis. There's a program of reverse mathematics which investigates how much of this comprehension you really need to prove standard mathematical theorems in analysis. And it turns out that in general, you need only very few or very weak comprehension schemes. Still, let's say, so if we have pi 1, 1, you have just one quantifier. So, and in pi 1, 2, you have one existential quantifier, but then, one universal quantifier, but then an existential quantifier. And actually, now it comes all this technical mess you have to work with. Oh, what happens if you still have a free set variable, but no quantifier? Things like that. The point here is that up to today, we are only able to give an ordinal analysis. So now taking other ordinals than this epsilon naught and bigger ordinals up to pi 1, 2 comprehension due to Ratien and array. I mean, array even goes a little bit further, but yeah, okay. What you need is to extend the method of Gensen very, very strongly. You need bigger ordinals and more things that sorry, go back here. So we have a least ordinal which is somehow the fixed point of this omega powers. And similar constructions, you need to get higher and higher ordinals. I mean, why is this epsilon naught? Well, then you can put epsilon 1, which is the next fixed point here, which is not epsilon naught, and so on. And then you can do the limit of this omega n's or omega alphas and so on. And you go further and further, but there come intrinsically more complicated things, actually, due to the impredicativity. What the moral is, if you do ordinary analysis, that some of the complexity of your set constructions, as we can say now in analysis, has to be mimicked by the ordinal notation system. Still, let's say it was an impressive result that we can give ordinal analysis for impredicative systems. It's weak compared with full analysis, and it's, I mean, completely out of scale if you think of set theory, which is far beyond that. So to put it together for analysis, modern proof theory relies on quite sophisticated methods, in particular to deal with the problem of impredicativity. And I don't want to present you here these methods. I mean, for that, it's even interesting. So you probably have to study several years of mathematical proof theory to be able to deal with these methods. I mean, there's no king's way to ordinal analysis, but it's done and gives some interesting results. But okay, it turns out that other conceptual frameworks, as from set theory, type theory, or computability theory, allow to address the technical obstacles in an easier way. So now, if you just do it by this Jensen method, you get stuck in the complexity of the comprehension schemes. But it turns out that certain comprehension schemes of set theory are equivalent to, for instance, set existence axioms in Kripke-Platek set theory. So Kripke-Platek set theory, you might never have heard of it, but I mean, we usually know Zermelo-Fraenkel. No, Kripke-Platek, it's much weaker, because what you don't have the unrestricted power set axiom, which gives the full power to Zermelo-Fraenkel set theory. Now you have something which is somehow constructively controlled. It's some kind of constructive set theory. Nevertheless, that there is a specific constructive set theory which addresses the intuitionistic concerns and leaves out the tertium non datur. But okay, so the point here is just to give you an idea that when we cannot work directly with the subsystems of analysis, I mean, the equivalent theories in other mathematical formal realms. So, and I mentioned here Kripke-Platek set theory, explicit mathematics is a framework due to Feferman, theories of inductive definitions, constructive set theory, and Martin Löw's type theory. And why I mentioned that, you will see on the next slide. While some of these frameworks come with a specific philosophical aspiration, in mathematical proof theory, they are first of all valuable for their formal properties. I mean, this is a specific point on Martin Löw's type theory, who, I mean, really came with an intuitionistic idea that we have an intuition how to build up these types, higher and higher types in his type theory. And so Martin Löw, I think, would plainly reject the idea of a consistency proof for his type theory, because that is supposed to be intuitively given. Well, in turn, that means that if you believe in Martin Löw's type theory, you can use that to carry out consistency proofs for other systems, which would be in line with Hilbert's program, Hilbert's revised program. But, and this comes now, here comes the point why I said, well, we know that analysis is consistent or not. I mean, one may note that all these theories are by far weaker than Zermelo-Fraenkel set theory, the universally accepted framework for mathematics in general. So, I mean, all what we do here in proof theory, I mean, let's exaggerate it, it's a joke for set theorists. If you do Zermelo-Fraenkel set theory, of course, you believe in the consistency of that theory. And everything we do here can be, I mean, more or less trivially embedded in Zermelo-Fraenkel set theory. So if you believe in the consistency of Zermelo-Fraenkel set theory, I mean, there's no question for the consistency of all these theories. I mean, or if it's for other reasons, not the mathematical part, but maybe some strange coding or some strange type constructions. Now, I'm saying that because it might question the very rationale of consistency proofs. I mean, if you believe in Zermelo-Fraenkel set theory, why you still want to have a consistency proof in the terms of Hilbert's program for full analysis? Well, we come back to that. Now, just let me show you, I mean, I want to give a snapshot of the landscape of proof theory, just that you see how we technically work. So here we have this ordinals. And of course, let's say, I mean, here this epsilon naught, I still sketched what it is. But I mean, now it comes with abbreviations, gamma naught, psi, omega. I mean, these are notation systems. Of course, you have to know how this is defined. Yeah, and let's say, what are these lines here? So this is a line when you go beyond that, you are essentially impredicative. And this, as I said, something has to mimic in the ordinal notation systems the complexity of that impredicativity, and that's actually done by so-called collapsing functions, which are in that psi. And here, to go to impredicativity, it's actually that this theory of inductive definitions, you have just one inductive definition, that is the first, I mean, fundamentally impredicative theory, and then you can iterate certain processes and you go further. Now, this is the predicative part, which, I mean, where you somehow can still avoid impredicativity, so that if you define a set, you don't refer to that set. There's an interesting area in between that was called metapredicativity, where somehow your set constructions might be already impredicative, but somehow the ordinal analysis can be done with the same methods you used for predicative systems. So you keep somehow you reduce the impredicativity of the set construction to predicativity in the notation systems, or in the treatment of the ordinal analysis. Okay, what you just see here in the middle is that Kripke-Platek appears to be the most successful framework to go further and further, and it is indeed, because then certain impredicativities which get really hard to control in the comprehension axioms, so the CA is always comprehension axiom, become more natural in the set theoretic effect. So this is just, let's say, to give you an idea where the technical work goes. But the remaining time of the talk, I will devote to further philosophical reflections. So if we look from a modern perspective, I started with the problem of Russell's paradox. And the paradox is there still such a problem? And now, I mean, you can listen to one of the leading set theorists of our days, Woody, I mean, who simply says, in the next 10,000 years, there will be no discovery of an inconsistency in these theories. And that is, he is referring to quite strong set theories. So it's Zermelo-Fraenkel set theory with inaccessible cardinals and some Woodian cardinals on top. I mean, that's completely out of reach for the ordinal analysis for the theories we have here treated with or studied in terms of ordinal analysis. And so, I mean, of course, the business of consistency proofs in terms of Hilbert, I mean, are meaningless for people which have a conviction like Woodin, if the objective is simply to show the consistency of the theory. But by the way, I mean, it were Hermann Weyl who still kept that opinion that analysis might be a house built on sand, and even Gensen, who said, oh, but I mean, maybe a contradiction is concealed in analysis. I mean, one of the points here is, I mean, Woodin doesn't say that there is no, but I mean, even in 10,000 years, I mean, if there would be one, we would not discover it. The point, of course, is that it might be concealed in an area which mathematicians don't touch. And by the way, if that would be the case, what would happen? Yeah, we would rearrange our set theory, that area is cutted and the part which is used in mathematics stays alive. That actually happens literally with Frege's inconsistent system of the Grundlagen der Arithmetik. Now, Gaisi Takeuchi, a proof theorist in the second half of the 20th century, expressed it, I would say, more modest than Woodin, but said, in the current day, axiomatic set theory is fully accepted, and it is generally acknowledged that modern mathematics can be carried out in the framework of axiomatic set theory. No contradiction has arisen in axiomatic set theory, and a sense of security that no contradiction will arise in it in the future is supported by intuitive consensus. Under the current secure circumstances, one cannot imagine the sense of crisis of that earlier time. So what he actually says, I mean, okay, well, empirically, we came to the conclusion, I mean, there is no contradiction. I mean, that's more or less in line with Woodin, but I mean, he also admits, let's say, that there were a sense of crisis around 1900. Just let's say that we cannot imagine what was going on there. And by the way, part of the shift of, I mean, feeling of security is based on the successful part of Hilbert's program, namely the formalization, the reduction to set theory, and I mean, that we were playing around enough with formal and informal proofs to get this sense that there should be no contradiction. Still, let's say, Takeuchi admits that for Hilbert and contemporaries at that time, the situation was different. So maybe there is no problem. But if there is no problem, does provide consistency to prove any added value? I mean, Hilbert, I said, I mean, it's quite clear from the writings that his main objective was to convince Brouwer and Weil. Well, by now, of course, they also passed away. I doubt that he convinced Brouwer. He might have convinced Weil. But of course, let's say the question is, I mean, if he convinced the mathematical community in general, and for instance, I mean, he definitely convinced Bourbaki that there are no consistency concerns. So is the job done? So why we should still do consistency proofs? I mean, even if it was not done in the way he imagined, but let's say that the problem was, I mean, that it's simply outdated. The interesting thing is, and that is the lesson I want to sell you here at the end of the day, no, there is still an added value. First, consistency proofs as such might not have enough added value. And Georg Kreisel, also a proof theorist of the second half of the 20th century, I mean, still lived into our century, but died a couple of years ago. I mean, he put it quite distinctively, the doubts about the consistency are more doubtful than the consistency itself. So if you do consistency proofs to convince somebody who has doubts, I mean, you may study the doubts first and realize, I mean, that's more doubtful than anything you can do about the consistency or what you could doubt about it. And that, by the way, I mean, here comes that point. I mean, Hilbert never doubted the consistency of any of these systems. It was this problem to convince other people and beat them on their own game. But let's say what Kreisel says here, I mean, even their game is more doubtful than the normal mathematics. But now in a technical point, and this is indeed, I mean, a quite debatable criticism. Solomon Pfeffermann, also a proof theorist who worked mainly in the second half of the 20th century, also died a couple of years ago only. Even if one succeed in reducing the system pi1-2 comprehension, plus minus bar induction, that is still an extra principle, to a constructive system, whether evidently so or not. And so let's stop here shortly. So constructive system, that are the ordinals. And so for epsilon naught, what I it's the idea that they are evidently constructive. But now, if you go to Pi 1-2 comprehension, and also there are a couple of papers Michael Ratin published on that with ordinal notation systems, which become more and more complicated, that the people, I mean, in the sense of Kreisel, might have more doubts about the um, ordinal notation system than about Pi 1-2 comprehension. In any case, let's say, I mean, one would most likely admit that the notation systems needed here are not so evidently constructive. Okay, but even if it's just a constructive system which is not evident, but let's say after hard work, you may prove again from a meta level that that's nicely constructive. Well, so even if one succeeds with that, one can hardly expect that doing so will appreciably increase one's belief in its consistency if one has any doubts about that in the first place, in view of the difficulty of checking the extremely complicated technical work needed for its ordinal analysis. So what Feverman says, I mean, this idea of ordinal analysis becomes so complex that in itself, it cannot increase the belief in consistency for a system, which might be impredicative and things like that. But I mean, where the complexity is shifted to the other level. That was my idea to tell you that somehow in Gensen's proof, you shift the complexity of universal quantification in induction somehow to the well-foundedness of epsilon naught. Here, you would shift the complexity of the impredicativity to an extremely complicated ordinal notation system. And so Feverman says that, I mean, he does not expect that increases the belief in the consistency. So, I mean, you do something there technically, you do good mathematical work, that I think he doesn't question, but it does not fulfill the objective of a consistency proof to increase the trust in a system, because you don't use a system which is more trustable than the one you investigate. Well, I put here in quote the subtitle, "Consistency is not the question." I mean, modern proof theory actually diverted from that. That's consistency is not the main point. And Angus MacIntyre, general mathematician from Great Britain, put it very nicely on record. Much nonsense has been pronounced about Gensen's work, even by extremely distinguished people. Consistency is not really the main issue at all. He did reveal fine structure in the unprobability of consistency of PA as a consequence of a much deeper general methodology. So what's the point here? It's not that we have a consistency proof of PA. In fact, I mean, but I think that is common sense. I mean, nobody questions, I said some mavericks maybe, but essentially nobody questions the consistency of PA. Now, Gensen pointed out that his transfinite induction is more reliable than the induction principle of PA, but still, let's say that's not the point. What MacIntyre says is that, oh, we get some extra value, I mean, not concerning consistency, but some fine structure about unprovability, because I mean, actually we can measure that with ordinals, and these ordinals give us information. For instance, actually, this is out of a text which then continues. Then you can use that to measure the growth rate of functions. Well, he also points to the much deeper general methodology. Let's say that it's not just one result. By the way, if you take the double negation interpretation, you have a single double negation interpretation of PA in Heyting arithmetic. You don't get any extra information. But here, I mean, you can really work with these ordinals and with the unprovability, let's say, what I said, where was the Gödel point, that transfinite induction up to epsilon naught is unprovable in piano arithmetic. That gives you some more information. And two more citations now, both directly directed to Schütte and his school. So Kurt Schütte was actually formerly the last doctoral students of David Hilbert, but effectively he was a student of Bernays. And after, I mean, in the second half of the 20th century, he had a proof theoretic school in Munich, which were still pursuing this ordinal analysis. And Michael Ratjen, for instance, I mean, considers himself a student of Schütte. Also, he was in Münster then. Okay, and Takeuchi writes, one characteristic of the Schütte school, so the school which for a long time were carrying out ordinal analysis, is that they shelve the troublesome problem of Hilbert's program, which is entangled with Gödel's theorem, and confine themselves to the theme of determining the proof-theoretic ordinals of formal systems. So that was somehow when I showed you the landscape. I mean, they were the real objective was the left column to get these ordinals, but not, let's say, to get philosophical reflections, and then they are shelved. And Wilfried Buchholz, a student of Schütte, wrote that more concretely. Since the beginning of 1950s, Schütte developed proof theory into a structure theory of mathematical proof possibility, independent of the problem of foundations to a large extent. So, and what I want to highlight here, and we inch to the end of my presentation, is this structure theory of mathematical proof. Because I mean, that is actually what proof theory aiming for. So now let's answer the question, what are consistency proofs and what should they be? And it's somehow Bernays in his last, I think, essentially last lecture when he got the Dr. Honoris Causa in the University of Munich 1 year before he passed away, expressed that. I mean, he summarized that. And I mean, he was the collaborator with Hilbert on Hilbert's program. So he is clearly the highest authority. And he recognizes that proof theory has taken a different development than Hilbert had imagined. Hilbert's proof theoretical program resulted in the task of proving the consistency of parts of classical mathematics from the finitist standpoint. As we know, due to the results of Gödel, this task had to be weakened to the extent that such a consistency proof can only be asked from an extended standpoint of constructivity. So that revised Hilbert's program. The effect of consistency proofs is, admittingly, hardly as it was originally intended by proof theory, namely to increase significantly the evidence of the classical theory. So it's hardly that. So here he somehow supports Fefermann's view expressed much later. The significance of these proofs actually does not lie in to arouse the conviction of consistency. Rather, such a proof shows something more far-reaching than consistency. And that is the point here. There is a part of the answer to the main question. So we want to do something more than consistency with consistency proofs. Proof theory has extensively developed, and the consideration of proof theoretic structure proves fruitful for mathematics itself. So combining the sentence before, the citation before that, we have a structure theory of proof. Now, consistency proofs help, to be fruitful for mathematics itself. And here comes, I think I found it only recently, actually. Kreisel published it, I think, in his last paper, a memory which summarizes that. According to Bernays, so Kreisel writes, according to Bernays, Hilbert was asked if his claims for the ideal of consistency should be taken literally. In his then usual style, he laughed and quipped that the claims serve only to attract the attention of mathematicians to the potential of proof theory. And so if you think this comment of Hilbert, which I take for granted that it's correct, we actually get a quite specific view on consistency proofs, which can be summarized as such. So consistency proofs are the core of a structure theory of mathematical proof. They reveal fine structure in the unprovability or probability of different formal theories. They require tools and techniques which are of independent interest and which provide additional insights. And in particular, they are today of mathematical interest rather than of philosophical. And so that is somehow the message I would try to sell you. And I thank you for your attention. Thank you very much.